Okay, and for our last panel of the day, we're going to be talking about propulsion systems development. And chairing this panel is my friend Mary Beth Koelbl, who has been working at NASA since birth. I thought it was always going to be in propulsion. She told me it was always going to be in propulsion. But she is now the Deputy Director of the Engineering Directorate. And she and I have worked together on very many agency level, center level panels, and she's got a great sensibility of what the agency needs to do and move forward, and especially here in propulsion. So Mary Beth, I'm going to turn it over to you and let you introduce the rest of your panelists. Thank you.
Thank you. He's right. I thought I was always going to be working in propulsion, and here I am not. So it's taken some getting used to. So I'm really glad to be chairing a panel in propulsion, because that's where I spent 33 years. So anyway, today I have 4 great panelists. I'm really excited to have them talk to you about what they're doing at their companies in propulsion. First, we have Brett Alexander. He's the Vice President of Government Sales and Strategy at Blue Origin. We have Dave Chaves, the Director of Space Systems and Advanced Programs at Moog, working with Mary, and Tom Martin, Director of Space Business Development at Aerojet Rocketdyne, and Kent Rominger, Vice President of Omega Capture of Northrop Grumman. And I'm going to let each one of them give a little intro of what they're doing in propulsion at their companies with a few slides, and then we'll get into the Q&A.
Thank you very much, Mary Beth. Let's see. All right. So just real quickly, Blue Origin is about a little over 2,000 people now, growing fast. When I joined 10 years ago, we were about 75 people. So we've been ramping up quite a bit, doubling in size every few years in the last decade. But I really want to point out our Huntsville, Alabama location, which over at Cummings Research Park, you'll see a very large building going up. And in fact, I hadn't seen it since it was just a foundation, and it's much, much larger than I had expected just by driving past it. So we have selected Huntsville to build a factory for manufacturing and producing our engines. We'll build the BE-4 and BE-3U engines, which will be used on our New Glenn launch vehicle. BE-4 will also be used on ULA's Vulcan launch system. And just down the road in Decatur. But we'll also be, we have taken over Marshall Test Flight, or Test Stand 4670 to do testing of engines, the acceptance testing of the BE-4 and the BE-3U engines there as well, just across the road at Marshall. So the engines that we produce right now real fast, BE-3 is flying our new Shepherd vehicle. BE-3U is a hydrogen upper stage variant of the BE-3 that will go on New Glenn. BE-4 is a LOX methane first stage engine that is the 550,000 pounds of thrust, and the BE-7 is our new lunar lander engine at about 10,000 pounds of thrust. Let me just real quickly show you each of these engines. The BE-3 has flown to space on 11 missions of New Shepard. 2 engines have done 5 of those flights each, so each one did 5 flights to space and back, and that's a relight of each engine as it lands down. Our BE-4 engine, sorry the font got messed up here, but the BE-4 engine is 550,000 pounds of thrust. We've tested it at full power already, 102% in fact, and thousands of seconds of test time on that engine so far. And these are all being tested down in our Texas site before they will start, I think next year, if not the year before, being tested at Marshall 4670. Our BE-3U upper stage engine, we did some back-to-back turbine testing that you see on the left there. And then we've added to the back-to-back turbine a thrust chamber demonstrator that you see there in the middle as well being tested, and thousands of seconds of test time on that as well. And then our BE-7 lunar lander engine, in May we unveiled this large mock-up or full-size mock-up of our Blue Moon lunar lander, and over the summer we did 2 different test campaigns on the BE-7 engine at Marshall. This is one the latest tests, and that's an IR video of the test. It's 10,000 pounds of thrust over at being tested at Marshall. So with that, I look forward to your questions.
Okay, next, Dave's going to talk about Moog.
All right, thank you, Mary Beth. I'm Dave Chaves with Moog, and when I come to forums like this, I'll introduce myself and somebody will say, oh, I know Moog. And I say, and the next thing out of their mouth is, oh, I know you for one of two reasons. One is I know you for actuators. And so, yes, we do actuators. We've been doing actuation essentially since the founding of the company back in the 50s. Traditional hydraulic actuators. At the turn of the century, we got into electromechanical actuation, and if you happen to watch the Apollo 50 landing, I'm talking about the turn of the 21st century, not the 20th century. And most recently, electrohydrostatic actuation. So was on Ken's static fire test. We had an electrohydrostatic actuation TVC system on that. The other answer I would get when I ask, or when I introduce myself and say I'm from Moog is, oh, I know Moog, you make valves. And so yes, along with motion control, we do fluid control as well. So we make valves for different size engines, for in-space engines. We make valves for liquid launcher engines. We make cold gas thrusters, a lot of different components that are used on the engines themselves. But I think maybe you don't know Moog for some of the other things that we do. So along the way here, we've acquired some additional technologies, and just want to talk about those for 1 minute. We have electromechanical actuation that is for on-orbit use that can go for anything from a solar array drive to a gimbal assembly on an electric propulsion engine. We make motors, slip rings, fiber optic joints down for kind of the tier, one tier down. We also make a lot of vibration control equipment. So soft ride is to isolate payloads, full payloads. We also isolate components on orbit, as well as make the ESPA ring, which most people are familiar with. In 2012, we purchased Ampact ISP up in Niagara Falls. It's about 30 miles away from our headquarters, and so we also do, so now we are in the small thruster, the on-orbit thruster business, as well as making tanks and small propulsion subsystems. And then lastly, we purchased Broadreach Engineering, which makes on-orbit avionics. Some of the advancements that we've been working on most recently, so we have an additive manufacturing center at our facility in East Aurora. We have about 15 additive machines as well as a full-up materials lab to go with that. So we've been doing a fair amount of research on in the additive manufacturing area. We've looked at, in the lower left there, you see an additively manufactured injector for one of our engines. We've actually also, the next picture kind of coming around at the 10 o'clock point there is an additively manufactured CubeSat size, a 1U complete propulsion system. It has a rolling metal diaphragm tank that was additively manufactured, built within it. So that's kind of us just, it's not quite ready for prime time, but we're working on it. Another area is down in the lower left, you see some fluid couplings. So we do a lot of the valve work. We're looking to do couplings for on-orbit servicing in the future. So we think we can support that piece of the industry going forward. We have a fair amount of capability in high-power electronics. We've kind of acquired that or built that capability over time, driving our electromechanical actuation systems. And so we've leveraged that into a very high efficiency DC-DC converter that can be used on applications like a PPE or wherever we need to convert high power. Lastly, we've kind of taken that and put it all into one spot, take an OMV, put some propulsion in it, put some avionics in it, and you end up with an OMV, and I'd like to just close with a video of that.
Great, thanks, Dave. Next, Tom's going to talk a little bit about what's going on at Aerojet Rocketdyne.
Thank you, Mary Beth. So I have a recurring discussion with my dad. He's a business professor, has no space background, only knows what he reads about in the newspaper. And the discussion always comes down to his point, why is it so hard and why is it so expensive to do space flight? And my answer always boils down to, well, physics, Dad, and don't you know about the rocket equation? And then we changed the subject. But that conversation got me thinking, why is there such a disparity between my dad's perception of where we should be in space flight and my perception, maybe a little bit more insider information on why we are where we are. And it occurred to me that the public has a general perception of technology advancement shaped by all the things that have happened in the information side of the world, the iPhones, all the things we do online. And that's fundamentally been driven by the microprocessor and the incredible increase in power with that. So I thought it would be interesting to see how a propulsion organization is doing against the benchmark for technology advancement. So I pulled this plot up of microprocessor power increase, and we all know Moore's law, right? Every 18 months, processor power doubles, and that is a logarithmic scale there on the y-axis. And I thought, let's plot a good performance metric for liquid propulsion. In this case, I chose combustion efficiency of a LOX hydrogen engine. And I plotted it from 1975-ish to where we've gotten to today, and I was extremely disappointed. But then I said, well, that benchmark, that's the RS-25, the shuttle main engine, and in 1975, when it began testing, it was operating at a 99.9% C-star efficiency. So I thought, okay, maybe that isn't that bad. And you know, it turns out if you plot most of the important characteristics of liquid chemical propulsion, it's a similar line. So what's my point? I'm not sure I have one. First, I think NASA made a very smart decision in selecting the RS-25 and the RL-10 as the primary liquid propulsion solutions for the SLS, because quite frankly, you're not going to get much better from a performance perspective. We have 16 engines on RS-25 ready to go to support the first 4 flights of SLS. The new engines are in production right now. And similarly on the RL-10, the first ICPS engine is down at KSC ready to go. We've finished qualification on the first 4 engines that will go into the EUS upper stage. And from the performance perspective, our focus has shifted to focusing not on the performance, because there's, quite frankly, we're at a marginal gains perspective. We're focused on how do we reduce the cost, how do we improve the reliability, and how do we cut down on the lead time to produce these engines. And that's where the focus, at least in propulsion on the booster side, has focused on the additive manufacturing and other manufacturing technologies that can accomplish those objectives. That's where RS-25 is starting to leverage additive manufacturing in its design. RL-10 recently is moving to what we call the CX configuration, where we've got a fully AM'd combustion chamber and injector. So that's where our focus is on propulsion. Second, since this is a panel on new propulsion, if chemical is kind of tapped out, and don't get me wrong, chemical propulsion remains incredibly challenging to do, especially booster propulsion. We gotta tap new sources of energy for our propulsion, and the obvious ones are solar and nuclear. And so from Aerojet Rocketdyne's perspective, that's where we are focusing. And the one advantage we have there is a lot of the focus now is how do we operate in space. Having a greater than 1 thrust to weight ratio remains critical for launch, but once we're in space, we have a little more freedom. So that's where solar electric propulsion is becoming extremely important to our business, and I think to NASA's plans. It is not something that is new to us. We've been flying very high power systems on national security and comms. We're working with NASA very closely. And then nuclear. Nuclear's been around for a long time. There are no new ideas in aerospace, but what has changed? The ISP is roughly double the best chemical systems, but the big game changer is the use of low enriched uranium for the reactors, and that gets us through a lot of problems that you had using highly enriched uranium and all of the problems associated with that. As a propulsion guy, I think it's also really cool because it actually looks a whole lot like a conventional engine. On the right there is an upper stage RL-10. On the right is a 25,000-pound thrust NTP engine that we've been working with Marshall and partners like Dynetics and BWXT. And if you get past the challenges of the reactor and integrating it into the engine cycle, the rest of it, it's all hydrogen. It looks like a lot about what we already know how to do on upper stages. So pretty cool. So we're really looking towards the in-space is where we advance the technology. Booster propulsion, upper stage propulsion will remain the core of our company, but it's marginal gains. If we want to do game-changing stuff in propulsion, we got to focus on the in-space stuff, and a lot of that is we're working directly with NASA on. The next C program, the AEPS thruster program, the 100 kilowatt next are all enabling, and particularly if we're talking crewed Mars missions, eventually NTP I think is going to be extremely important. So, thank you.
Great, thanks, Tom. And last, Kent, will you talk about what's going on at Northrop Grumman?
I would love to, especially if Tom hands me the clicker.
I'll even hit the button for you.
Thank you. Hey, so thank you all for coming today. What I'm going to talk a little bit about is what's been going on at Northrop in the solid rocket motor propulsion world. And probably the easiest way to describe it is through a launch vehicle, a launch system that we're developing, Omega. So we have a model outside in the lobby of Omega. It's not as well known as I wished it were. I'm the capture manager, so I'm here to give us more exposure. And the Omega system consists of 2 rockets, and they consist of solid boost. And the intermediate rocket, which will fly in 2021, is the smaller one you see at the lower left side of the screen. And our design is around a common boost segment. So in the propulsion world, we know the space shuttle motors were segmented. Space Launch System motors are segmented. So segmented motors are nothing new. What is new with these motors are the propellant that we're using and their composite cases. And so the composite cases give you a great strength to weight ratio. And on the larger motors, it allows us to run pressures that can give us better efficiencies out of these motors as well. The first stage is 2 segments, and out of those 2 segments, you roughly get a couple of million pounds of thrust. Our second stage is a single segment, and it's just under 1 million pounds of thrust. And that second stage motor is common between our intermediate and our heavy. And the reason we have 2 systems, or this system was designed to meet the Air Force's national security space launch missions. And they vary. They vary from fairly simple LEO missions to fairly complicated direct GEO missions with large, expensive payloads. And today what we see is we've got Atlas V, Delta IV Heavy that span that range, Falcon 9, Falcon Heavy that span that range. And so it really is to span that range. For best value, it makes sense to have a system that is not just a single rocket. In addition to the solid boost on the core, we have strap-on motors to augment it. So you can tailor the performance that you need for your payloads. And it's a GEM 63XL. The GEM 63XL is kind of a big brother from the GEM 63. The GEM 63 is being used by ULA for Atlas V. It's been test fired twice. The XL is a 5.5 foot longer version of that for our system. It's also being used by ULA. For propulsion on the upper stage, we've got the extremely reliable RL-10, very efficient RL-10. And again, when you're launching national security payloads, reliability of your system is very, very important. And so when we took that into account, we knew that we needed a system that would be very reliable. And the RL-10 is kind of the leading one on the globe. Also, we need to get it a plug for solid propulsion. You know, in the last 15 years, knock on wood, in the U.S. in space launch, we've had 100% success out of our solid rocket motors. Here's some shots that I think Tom and Dave will appreciate. Upper left is the GEM 63, just an inert, but to show you that motor being processed. To the right of it, kind of transitioning to the upper end of the rocket, that's the dome, the dome that's gone through qualification. We are manufacturing that at the Michoud assembly facility, not too far down the road. And then below it is some of Dave's handiwork, but the electro-hydrostatic TVC system. It's beautiful hardware. For those of you that love hardware, getting to see these actuators, they're absolutely gorgeous. Kind of transition to the right, it just shows a wind tunnel. There's the RL-10 going through qual testing back in November of 18. Which shows an igniter to light a solid rocket motor. You use a smaller solid rocket motor. That's the test firing of it. In May of 19, we test fired our first stage of a Mega, and we're happy to say several years ago we picked that quarter, and actually May is the time we would static test fire that motor. We held that schedule. And then to the lower right corner is a really cool thing, and that's Mobile Launch Platform 3 that we're going to use to launch out of the East Coast at the Kennedy Space Center. We're launching off of 39B, the same launch pad that SLS Artemis use. This mobile launch platform launched Neil Armstrong about 50 years ago on Apollo 11. I also, turns out, flew off of this mobile launch platform 3 times myself. Unfortunately, not going to the moon. But I put in a slide with large solid rocket motors. A lot of times I get the question, what about your ride quality? Isn't the ride really rough on large solid rocket motors? And the answer is no. We designed this system from the ground up to have very benign environments, because unlike a liquid, we can't throttle real time, so we have to design the system to meet all those ride requirements that come along. And in fact, so I expect you can't read that chart, but what it's showing you is we're within all the requirements. And if you pull handbooks from other rockets that are out there today, we actually have a smoother ride than those other systems. Lastly, this technology we're using on Omega, turns out our motors are the same diameter as those on Shuttle and SLS. And so it has great applications to the booster obsolescence for SLS. So with that, I'll turn it back over to Mary.
Okay, great. Thank you all for your introduction about what exciting things are going on in your companies on propulsion. I'm just going to ask a few questions to get us started, and then we'll open it up to the audience. First, Brett, can you talk about, as our focus shifts from low Earth orbit to the moon, what do you think the gaps in propulsion technology are that need to be addressed?
So I think some of the other panelists also mentioned that, in space is very different from boost propulsion. And so in space, you don't need a thrust to weight of 1, but you really need to have high efficiency. And so, we're developing a LOX hydrogen engine, the BE-7 engine for a lunar lander for in-space application, as well as our BE-3U upper stage engine, which is much, much bigger at about 160,000 pounds of thrust. But the point was also made that nuclear propulsion is sort of, the ultimate of where we want to go, because it's important for higher efficiency and higher ISP in the long term. But in terms of NASA's Artemis program and eventual Mars missions, foundational for that is high efficiency LOX hydrogen propulsion. And so we've been working on that for over a decade now. So.
Okay, great. Dave, with all the renewed interest in space by NASA and the DoD we heard about today, how do you feel the country's industrial base and suppliers, are they strong enough to support all this future work? If not, what can we do to help?
So I can kind of answer that from a tier 1, 2 supplier kind of framework. I think the industrial base, I think we struggled a bit coming out of the late 2008 to whatever, 12, 14 timeframe. You had the retirement of the shuttle, you had DOD kind of winding down a bit, and I think the industrial base kind of went with that some. And I think to the point where many of the suppliers actually exited the business. So you kind of fast forward to a couple years ago, and suddenly space comes back, and it seemed to come back with a vengeance then. And so you look around and you go, oh boy, now what? And so I think it kind of caught the whole industrial base flat-footed. And so we're trying to recover from that. I think there's still a couple things that are driving against that maybe. One is, I think you look around, I know my company kind of is trying to figure out the answer, and maybe the government is too. Where is vertical integration going to take us in the future? And if it's going to, be the real wave of the future, then it's going to affect the industrial base for sure. I think that still has to play out some, and we'll see where that goes. I think another thing that we felt are the advent of the OTA. And so now the government is expecting companies to invest more heavily in their programs, and that's getting driven down to the next tier as well. So we've been feeling some of that. I think lastly, as we try and get back on good footing here, we feel the same thing everybody else was talking about in the session this morning, which is it's hard to get workers today, right? The whole economy's going great, space is going great. It's hard to go and recruit. So I think, there's kind of those negative pressures on it, if you will. But then on the, I think on the opposite side of that, there's a couple things that are certainly positive. One, when we had the discussion or the talk earlier today from SDA, you hear the word proliferation. Well, okay, that sounds like a good thing for us, right? I can put that word in front of my CEO and say, hey, space is, this is the good side of space coming back with a vengeance. So there is a need there. It sure feels like that's going to continue and gives us a reason to find answers to some of the problems. I think the other piece on the good side of this is all the VC or venture money that's coming into the industry today. It's driving a lot of new technology. It's driving a whole new vendor base, which will support space as a whole in a very large way in the future. So I think the industrial base will get there. I think it's certainly swinging on the upswing now.
That's great.
Yeah, Mary Beth, if you don't mind, it's an important topic for us too. And Aerojet Rocketdyne is kind of a merchant supplier, so and a lot of times we're in the middle as well, a supplier sometimes, a prime sometimes. But I think there's potentially some unintended consequences of where the government is headed with some of its new acquisition approaches and how that's going to affect the technology base of the industry as a whole. Moving away from this idea that the government funds technology for the good of the industry, owns that IP, and can distribute it where it makes sense based on the need within the government. Great examples for us is leveraging the shuttle activity across multiple product lines, RL10 across multiple product lines. RS-25 right now is supporting a DARPA program on XSP, a military application. But as the government's using more of these service-based acquisitions, one, those come with IP rights that basically mean whoever's bidding that owns the rights, and it also tends to produce a vertical integration approach. And so that money and that technology tends to get locked up in a vertical chain only within what that service is. So I think if there's going to be consequences long-term to how technology benefits the broader community if this trend of just buying services continues, and that's a concern that we have.
Okay, great. So, Tom, I had a prepared question for you, too, so you get double duty. Can you talk about propulsion technology for Mars, and is there some cross-cutting with the moon, or what do you think we should invest in a little further out?
Yeah, absolutely. And first, I need to give Rommel credit. He finally figured out that the thrust goes on the bottom and the performance goes on the top of the rocket. Now he just needs to figure out that he needs liquid propulsion on the bottom. I think Michelle Rucker said it really well in her talk earlier about how we get to Mars, and it was that we don't need to start from scratch. So our view of the best way to get to Mars, and there's lots of ideas, is kind of what we call a split architecture, where we use highly efficient solar electric propulsion to pre-position cargo ahead of time, 2 years out, like that. You know, the cargo doesn't really care about how long it takes to get there, so you pre-position it using the most efficient method, and then you follow on with crew delivery, where they do worry about how much time they're spending out in deep space using conventional propulsion. You know, SEP right now like I said, it's flying today. NASA's doing a lot of work to advance that technology to higher power levels. So I think that technology is really on the path there. We all know chemical propulsion is mature and can support that. And then long term, you know, the NTP as a way to really cut the transfer time down from, you know, 200, 300 days down to something like 140 days is significant, particularly with respect to crew health. So we absolutely see that we're on the right track for propulsion, and it's not, we don't see it as being a limiting factor.
Okay, great. And Kent, with limited budgets and lots of work in space, how can we make propulsion more affordable to enable successful missions?
Yeah, and I think there are several answers to that question, how you make propulsion more affordable. One that's been demonstrated lately is reusability. So you can reuse those pieces of propulsion that are expensive. And interestingly, for a mega, although in the space shuttle world we reused hundreds of solid rocket boosters, when we ran the business case, it turned out to be more affordable not to in that case. So another aspect of making things more affordable is actually prioritizing it, making it one of those design criteria that you have to meet. And a couple of decades ago, when I was at NASA, you know, we really cared about the best system. And affordability wasn't nearly prioritized as highly as it is today. Today, customers care about value. They care about a product that will meet their needs, but is affordable, right? And so we're seeing a lot of emphasis on value, which I think is a great thing. And how do you get the best value? Well, first of all, this system has to be reliable and work. But to control costs, you need to look really hard at your supply chain. And in some cases, it makes sense to bring the supply chain in-house where you can really control the supply chain. In other cases, hey, that's just too expensive, right? So it doesn't make sense for us at Northrop to design an RL-10, so you go outside, the same with Dave's actuators. But for the most part on a mega, we do that manufacturing in-house. The other thing it does, because we're obviously a very large, broad, customer-based company with many products, we happen to have the infrastructure in place in Utah where we build solid rocket motors for NASA, for the Air Force, for the Navy, for Missile Defense Agency, and for commercial customers. And given where we've been the last several decades, pretty much in most of our factories, we have excess capacity. So we're in a place where we can leverage the synergies, which are the people, the processes, and the infrastructure, to bring on another product for very affordable costs. So I think, you know, it's kind of a neat place in the world. And lastly, I mentioned prioritizing, but we do prioritize, right? So we make trades where maybe a piece of manufacturing piece that you're using on your system is ideal technically, but it's expensive. And there's one that's not quite as good technically, but much, much more affordable. You figure out how to have the reliability out of your product with affordability, and you weight that when you make those trades and design the system. So thank you.
Okay, great. Thank y'all. We're going to open it up to audience questions now.
Hi, thanks very much for the discussion. Dan Mazick, NASA Langley. I guess this question is to Kent. You just mentioned about, you did the numbers that showed that reusability didn't favor well. Is that germane specifically to the solid rocket motors? Or what's the rationale behind that?
So yeah, I think it's much different reusing a solid rocket motor versus reusing a liquid engine. And you know, the way we've recovered solid rocket motors in the past are, you've got to incorporate a parachute on them, flotation. We also severed part of the nozzle so it didn't get damaged during splashdown in the water. And so on Omega, when we looked at all of that and flight rates and the complication, and it does add a bit of complication and weight and hurt your performance, it really didn't pay for itself by the time you looked at the labor. And so in the liquid world, right, you'd probably let Brett answer that question. So, because it's a different beast.
Certainly, we've looked at it, and we believe reusability is the way to go, obviously. We're looking at a reusable booster system. We're flying New Shepard now, suborbitally to space, and first stage of our New Glenn rocket, which is 3.85 million pounds of thrust on the first stage, is also reusable and will land on a sea-based platform. I think, there are two things that sort of work against each other in terms of affordability. Reusability, which allows you to reuse the hardware, but you're getting less production rate. And so as your flight rate, if your flight rate stays the same, then your production rate goes down because the engines and the systems are reusable, and that sort of counteracts the affordability advantage that you get from reusability. But I think the ultimate objective really is to get through that trough of where we're doing, small tens of launches a year, or a company is doing 10 a year itself, and move that into the upper tens and hundreds of launches a year, where reusability and affordability and rate all play into it, and you truly have operable systems.
Yeah, Al Tadros Maxar. Along the same lines, you mentioned reliability for national security launches. I know a lot of launch systems are also looking at lower cost large constellations or disaggregated even government missions. Did the design of the Omega head down the path that it did specifically for a traditional kind of national security type of market, or is it also intended to address kind of the lower cost proliferation of disaggregated systems?
So actually both. And when the Air Force sent out the requirements for national security space, this follow-on phase, the requirements were, there were 9 reference missions, from fairly simple to very complicated. The size of rocket you needed varied a lot as well. But one of the requirements was your system had to be commercially viable. And basically the Air Force said, hey, we don't want to find ourselves in a monopoly situation where we're kind of the only customer. So if we're truly interested in your system, it needs to be designed to be affordable and service many more missions than just ours, the Air Force. So we did design Omega, and pretty much our intermediate version that has no strap-ons, our most affordable version, kind of hits the sweet spot on what we thought the commercial sector would want.
Let me add on to that in terms of reusability and reliability. Obviously, we believe that a reusable system is inherently more reliable because you're using the same hardware over. You know how it performs. If you think about an airplane, the safest airplane to fly on is the one that you just got off of, not the one that just came off of the factory floor. But along with that, the reliability is an outcome, or we're much more aligned with reliability based on a reusable system, because that first stage asset for us is a very high value asset. We need, as a company, we need to get that back. We cannot afford to throw it away every time. And so we are incentivized, if you will, to have the highest possible reliability, get that asset back. And that's much more in alignment with the payload customer, who really wants that to make it to orbit as well.
While I have the mic, a different question. I noticed the Omega has a 5-meter fairing. I think the New Glenn is 7-meter fairing, and I guess, what drove you to the fairing sizes for each, and is there a trend or not?
Well, bigger is always better. Honestly, the 7-meter fairing for us was driven by the fact that we have a 7-meter diameter already on the core and the upper stage. We initially looked at a 5-meter fairing as our initial offering, since that was what was the largest available in the commercial market and required by the Air Force for their program. But there was nothing really stopping us from going straight to a 7-meter fairing. Having that additional volume is certainly useful for those that are not, let's say, performance mass constrained, but are really volume constrained, like the proliferated LEO systems. And so we decided to go straight to that size fairing.
Yeah, and on Omega, we designed for affordability to meet the mission, and this 5.3 meter fairing does that. We have a couple different lengths that we did. Having said that, it's been interesting the last couple of years, and really because of New Glenn and a 7-meter fairing, we're watching the customers, and the Air Force being one of them, and we see them becoming more and more interested in the larger fairing. So in fact, I think Blue may be setting a new standard. So the good news is for us with the Mega is we have a factory not far from here that manufactures fairings, and we have the capability to manufacture 7-meter fairings. So the truth is on our heavy system, and I didn't talk about it much, intermediate flies in 21, our heavy's gonna fly in 24. This system is all about getting launched on time and being very reliable. With the Heavy, we have a few more years. We've got time and resources, including money, built in to incorporate some innovation. So we are evaluating if we in fact do have the right size fairing on the Heavy, but as of today, it's a 5.3 meter fairing. Good question.
So I'll ask one over this way. So a lot of talk about nuclear thermal hasn't been tested on the ground for some time, but we like to talk about it. What are the chief challenges of putting nuclear thermal propulsion on to a vehicle to Mars, maybe in the next 10 years, the next 20 years?
Number one, I'd say perception is probably the biggest challenge, and that's why I talked a bit about the low enriched uranium as I think being a key element of what's different from when this was done back in the 1960s and 70s. So I think that's going to be a key one in terms of the regulatory regime. Fundamentally then demonstrating that the reactor, can do what it says. We, from the engine perspective, there are challenges, but it's fundamentally flowing hot hydrogen through an engine, and we know how to do that pretty well. I said, from a stage integration perspective, it integrates a lot like a conventional engine, and it's hydrogen. So the other aspect is, particularly for something like a Mars mission, cryo fluid management, having the hydrogen there 2 years later when you want to head back to Mars, to Earth is another key challenge there. But I think the biggest is the perception that we can do it, and we can do it affordably, and I think that's where doing something that basically, there's a lot of talk all over the place about we need to do flight demos to show that we can do this, and I think getting to a quick flight demo that shows people this is a real technology that's not high risk is where we need to get to.
I would agree with that. I think the political will and the public opposition or possible opposition would be the biggest thing to overcome. Technically, we know we can do it.
Yeah, I'm on the solid guy, but I totally agree that it's a political challenge. And the other thing is, I think, once we kind of show the public, hey, now instead of 9 months to get a crew to Mars, it's a fraction of that. You drive the excitement and you show that, hey, if we're really going to start exploring Mars and beyond, you've got to have this kind of power source for those propulsion systems. And so I think we kind of have to lead the witness by getting them excited with the capability of what this system can do.
I'd just add, we talked a lot about space policy earlier today and how that's there might be some changes and regulations are getting lifted. So there's potential there to help from a regulatory and policy standpoint as well.
A question for Brett. You talked about reliability and flying the same booster over and over again. Well, we have a tremendous experience base with LOX hydrogen. We don't have such an experience base with LOX propane. So, or LNG,
Methane, yeah.
methane. So how are you going to make up, where do you see the risk in the shortfall of experience with LOX natural gas?
You know, I think fundamentally they're both hydrocarbons, you know, kerosene and methane, both hydrocarbons. We haven't found any significant issues in all of the testing we've done, thousands of ignitions, thousands of seconds of testing. So, you know, there are benefits in terms of no soot, no, you know, autogenous pressurization, and other things. So we haven't found any of those issues. Then it goes to the specific design of the engine, and just like every kerosene engine has its own specific design, you want to test it and test it and test it so that you get all the corners of the box figured out before you fly in that regime. You know, we're doing the same thing with our BE4 LNG engine. I think the other thing that you know, because we're designing it to be reusable, you know, up to 100 missions, which is 200 starts because it restarts on the way down, we're building in a lot of margin throughout that engine. The other thing is because of the way we've designed the flight trajectory, the ConOps, is we're not returning to launch site with the booster. We're flying downrange to a landing platform, and we're essentially going to fly the same path for the first stage every time, because it's the same vehicle, same configuration for no matter what's on top. We're flying that same path each time, which means we're hopefully flying down this, you know, the dead center of the box in terms of performance instead of maxing it out at the corners of the box and changing it all the time. So hopefully that will also add to that additional reliability factor from the reusable side.
Well, I think that closes up this panel. Thank you all very much. We appreciate it. Let's give the panel a hand.